This is a look at the magnetic force that's experienced by a charged particle moving in a magnetic field. So the charge has to have a velocity vector with at least some component of it perpendicular to the magnetic field vector, and when that happens, it creates a magnetic force, which is also perpendicular to the other two vectors. Now, that force vector is given by the charge magnitude, little q, times the vector product or cross product of the velocity vector and the magnetic field vector. Now, oftentimes in high school physics, it's not that deep. We're usually just solving for the magnitude of this force vector and then the directions found with the right-hand rule. So it's going to be the charge magnitude times the speed or the magnitude of the velocity vector times the magnitude or number to the field times sine of theta, which is the angle between the two vectors, velocity vector and field vector. And then oftentimes there's not even an angle given. Usually questions just give you a field perpendicular to the velocity vector, like in the picture I have on the right. So usually when you're in AP Physics 2, you're just doing charge magnitude times speed times field magnitude QVB. Now in the case where there is an angle between the velocity vector and the field vector, so like here, there's an angle theta between the two vectors. If at least some component of the field vector is perpendicular to velocity, then there will be a magnetic force, and that's when you do QVB times sine of the angle between them. The direction of the magnetic force on a moving charge is given by the right-hand rule. You keep all your fingers together and put your thumb perpendicular to the fingers, and in this case, the thumb's direction is the direction of the velocity vector for the charge. The fingers point in the direction of the magnetic field, and then the force would be directed outwards out of the palm. That looks like this. So for a field into the page, I point my fingers into the board, my thumb to the right in the direction of the charge's motion, and then the force would be upwards out of the palm. Now, positive charges are going to react to a magnetic field differently from a negative charge. So to find the direction of the force on a negative charge, you use the left-hand rule, which is the same rules as the right-hand rule, just with the left hand. So here, fingers into the board of the left hand, thumb in the direction of motion, but in this case, my palm would point down, so the force is opposite the direction it was for a positive charge. So I have an example here on looking at various combinations of velocity vectors and field vectors and finding the resulting force. The first one involves a negative charge, so I'll use the left-hand rule here. And if I take my left hand and put my thumb to the right in the direction of velocity and my fingers out of the page, then my palm will point up, so the force in this case is directed upwards. The next one's a positive charge, so it's going to use the right hand. So here, the right hand has the thumb pointing down, fingers into the page, and then the palm would be facing to the right, so the magnetic force is to the right. Here's another positive one, thumb to the left, fingers out of the page with the field, and the palm is pointing up, so the force is upwards. The next one is a negative charge. My fingers are pointing down, thumb to the right, and the force is directed out of the page. E, I have a positive charge, fingers to the right in the direction of field, thumb down in the direction of the velocity, and again, my palm is pointing out of the page, so the force is out of the page here as well. The last one is not actually possible to do with the right-hand rule because the velocity is anti-parallel to field. So in this case, there's no force. And in order for there to be a force, at least some component of the velocity vector has to be perpendicular to the field vector. Example B is a two-step question asking for the direction and magnitude of the magnetic force on a negative charge moving downwards towards a wire carrying current to the right. Okay, so for this example, I'm going to find the direction of the magnetic field above the wire. So for that, I'm going to use the right-hand rule, thumb in the direction of current to the right. And when I do that, my fingers are going to curl out of the page above the wire. So the magnetic field above the wire is going to be out of the page. And that magnetic field is going to have a field magnitude of mu sub 0 I over 2 pi r. And then to find the force, the direction of the force, I'm going to use, since it's a negative charge, I'm going to use the left-hand rule. If I point my fingers and my left hand up, and my thumb down, my palm points to the right. So the magnetic force here on this charge will be to the right. The magnetic force magnitude is given by QVB. In this case, Q is given as Q, V is given as V, and then the magnitude of the field is mu sub 0 I over 2 pi r. So my answer for magnetic field is that. It's QV mu sub 0 I over 2 pi r. So the force here is to the right, but as the force acts on the charge, it'll change the direction of the charge, which will also then change the direction of the force. Because the magnetic force vector is always perpendicular to the velocity vector, a moving charge in a constant magnetic field is going to travel in circular motion. So if we look at a positive charge moving up in a field directed into the page, as it goes up, the force is going to try to turn it to the left until it looks like this. So it's going to try to go to the left, but now by the right-hand rule, the force is down. Now once it's going down, there's going to be a force to the right. So as it goes down, it's going to try to turn to the right. And the result is circular motion. Now in circular motion, there's always a force perpendicular to velocity, and that's exactly what happens when there's a magnetic force. The magnetic force is always going to be perpendicular to the velocity vector of the charge, which causes uniform circular motion. And because the force is always perpendicular, a magnetic force will change the direction of the charge, but not its speed. One thing to note is that perpendicular forces don't do any work. So a magnetic force will never do work on a moving charge, which means it'll never change the kinetic energy of the moving charge. So when there is a charge moving in a uniform magnetic field, and it does have to be a uniform field for it to be in circular motion because that's when the force magnitude stays the same, the magnetic force magnitude QVB can be set equal to mv squared over r. So QVB, that's the net force, because there's only one force, the magnetic force, and then mv squared over r, what I have here is just a statement of Newton's second law. So F equals ma, m is mass, and then v squared over r is something called centripetal acceleration, which is the acceleration that's keeping something in circular motion. I can cancel out the v squared on the right with the v on the left, and there's sort of two ways to write this in terms of what's being asked in high school physics. Oftentimes questions will talk about something called the mass to charge ratio, or m over q. And if I rearrange this, I get that ratio is going to be magnetic field strength times the radius of the circle over velocity. Another thing that's often asked about is the radius of the circle. So if I solve this for r, I would get mv, mass times velocity, over bq. A common situation in AP Physics is for there to be a moving charge in the presence of both an electric field and a magnetic field at the same time. When both these fields act at once, the combined force of the electric force and the magnetic force is called the Lorentz force. Now, assuming the field is perpendicular to the charge's velocity, the force is just QVB, and then the electric force is EQ. Now, when these two forces equal each other, the charge will pass straight, undeflected, through both fields, and that's going to be when the velocity is the electric field strength over the magnetic field strength. The magnetic field strength is based on velocity, so when the velocity was e over b, the particle went straight. But if a particle is going slower, then that's going to mean the electric field is stronger and the particle will curve in the direction of the electric force. Now, if the particle is traveling faster, that's going to make the magnetic force stronger, and in this case, the particle is going to curve in the direction of the magnetic force. Okay, last example is a pretty common type of question. It's a situation that represents a mass spectrometer. And there's three parts to this question. In the first region, there's going to be a voltage applied to the charge, which is going to accelerate it from rest. Then it's going to go to region 2, where it's going to travel straight due to opposing magnetic and electric fields. Then in region 3, there's just a magnetic field, so the particle is going to curve in circular motion. The question asks for a few things. It asks for the potential difference in region 1. It asks for information about the electric field in region 2, for the particle to go undeflected, and then for the radius in region 3 when the particle curves in circular motion. Okay, in part A, the particle starts at rest, and then it's accelerated by a potential difference. So I'm going to use the work-energy theorem to solve for the potential difference applied here. So for the work done by a voltage on a charge, that's the change in potential, delta V times Q. And that's going to be the final kinetic energy minus the initial kinetic energy, which is 0. So then my voltage is mv squared over 2Q. And now I just plug in numbers. And that gives that the voltage is 1.0 times 10 to the 6th, or 1 million volts. The next part pertains to region 2, and it asked about the electric field. So the particle travels undeflected, which means it has a straight path through region 2. And the electric force is going to have to be in the opposite direction of the magnetic force. So first I'll find the direction of the magnetic force. So it's a negative charge. So I'm going to use the left-hand rule. So I'll take my left hand, point my fingers into the page, and my thumb to the right. In that case, my palm would face down. So there's a downward magnetic force, which means there has to be an upward electric force. And this is where questions often will try to trick you. Since the electric force is up and it's a negative charge, that means the electric field in this region has to be down. To find the actual magnitude of it, the net force is the upwards electric force minus the downwards magnetic force, and it equals 0 because it's undeflected. So electric force is EQ, and magnetic force is QVB. The Q's cancel, and I get that the electric field strength is equal to VB. And that's going to be 1 times 10 to the 6th, or 1 million newtons per coulomb. In the third region, the particle is going to curve, and it asks to calculate the radius of curvature and which way it curves. So for the direction it curves, it's the left-hand rule again. So the particle will travel straight, then left-hand rule, fingers out of the page, thumb pointing to the right, and the force would be up. So the particle is going to curve upwards. And then for radius, I'm going to set the magnetic force equal to the centripetal force, because the magnetic force is providing centripetal force. Magnetic force is QVB equals mv squared over r. I get that r is mv over qb. And then the radius is 1/2, and the particle curves upwards.